Hello everybody. Today we will be solving Leetcode 3243, shortest distance after road addition queries 1. Before I get started, I want to let you know that I will be providing two different solutions in two different videos. In this solution, we'll be using breadth first search, whereas the next video, I will be using dynamic programming, which will be somewhat quicker and provide a faster or better time complexity. The reason why I don't add them both here is because I prefer to keep my video solutions short. The longer they are, even for myself, it's hard to remain focused and dedicate my true full mental capacity. So I think most people are the same. Um, so here we go. So what they're asking us to do is they give us n, which is an integer, and they tell us directly that the the nodes are unidirectional. And I say node because we can view this representation as a graph. So each node initially can travel only to the next node. They also give us a queries two-dimensional array or list where each element of the query is an additional edge, or what they call a road. But let's view this as a graph theory problem. So initially we have the nodes 0 to 1, 1 to 2, 2 to 3, 3 to 4 with those edges. They give us an additional edge for query 1. So they're telling us that now 2 can travel directly to 4. And for the next query, they tell us 0 can travel to 2. And on the last edge, or additional query, they tell us 0 can travel directly to 4. All along, they want us to calculate the length of the shortest path from city 0 to city n-1. So they want to know, after this first query here, what is the distance from 0 to 4? Originally, it would have been 4, right? Sorry, 0 to 1 is 1, 1 to 2 is 2, 2 to 3 is 3, 3 to 4 is 4. So it would have taken 4 steps. However, with this additional edge from 2 to 4, we can now travel from 0 to 1, 1 to 2, which is 2 steps, but 2 to 4 directly, which would give us a shorter path of 3. And for this next query here, they tell us 0 can travel directly to 2. So considering this new graph and these edges, what is the shortest path from 0 to 4? So we can either travel from 0 to 1 or 0 to 2. And then, so it makes more sense to travel to 2 if we're attempting to find the shortest path from 0 to 4. And again, 2 is the option from traveling directly from 2 to 4 or 2 to 3. And again, it would be better to travel directly from 2 to 4 if our goal is to find the shortest path. So for this instance, with this new graph with these edges, the shortest path would be 2. Lastly, with this last new edge or road, we can travel from 0 to 4 directly, or 0 to 1, or 0 to 2. But it's far quicker, and the shortest path is revealed if we travel from 0 to 4, which would give us a result of 1, which is what they get here. So that's basically the problem. We're going to use breadth first search, and it should be straightforward. So let's go through it together. So what I'm first going to do is create a graph that has the initial representation that looks something like this, because this is what they give us. So notice the neighbor of 0 is 1, it only has one neighbor. Neighbor of 1 is 2, neighbor of 2 is 3, neighbor of 3 is 4. So let's create a graph of this. So this will be holding our graph and graph representation, which will be an adjacency list. And now let's populate the neighbors for each node. So for I in now notice I'm only going to n minus 1. I'm not going to go to the last node because the last node does not have any neighbors. 4 doesn't have any neighbors. So it just makes sense to go to the next to last node. And notice how every node, the neighbor is 1 bigger than its current value. So we can do something like this. So g of I, and then we're going to add what? So remember, the neighbor is always 1 value bigger, so we'll just add I plus 1. Okay, there we go. Another thing we want to do is, remember, we're going to loop through each of the queries, or what I would just relabel as edges, and perform a breadth first search to calculate the shortest distance considering each new edge. So let's write that down. So for u comma v in queries, we'll perform breadth first search. So let's before we perform breadth first search, we'll want to add the edge to the graph. So g of u dot add v. So 2, 4, this new edge goes from 2 to 4 here. And we'll want to, once this edge is introduced to the graph, now we will perform breadth first search. So let's perform breadth first search. And we're yet to define breadth first search yet, and we'll return the number of steps it takes. So we'll just call this maybe call it steps, and we'll just add it to the result. So result dot append steps, and then at the end we'll return the result. Okay, so now let's define breadth first search. So for breadth first search here, we'll be using a queue, or more specifically a double-ended queue. And we always know for our problem, they ask us to find the path from 0 to n minus 1. So we always know this starting node will be 0. Okay. And in order to perform our breadth first search, we want to keep track of which nodes we've visited. And we'll start off with visiting our node 0. And just as a quick pointer is that normally these 2 italics or curly braces, they indicate a dict, but when you write it in this form, it indicates a set with a single element of 0. So just wanted to point that out to you. We'll also want to keep track of number of steps, and well, for now there take 0 steps. Okay, so we'll keep searching while the queue has elements in it. So while queue. And so we'll want to search the neighbors of 0. So let's search the neighbors of 0 for underscore and range length of queue. I'm moving on. So we'll pop, or we'll remove that first node in our queue. So we'll perform queue.pop left, and that'll be the node that we're currently at. So this would mean that we're at node 0. And then we'll want to loop through all the neighbors of 0 or the node and add that to our queue, assuming that we haven't visited it before. So for each neighbor in, so g of node. So in this case, it would be g of 0. Now, if the neighbor is not in v, then we'll add it to our queue. So queue dot append neighbor, and we'll also add it to our visited set. V dot add neighbor. Once we've finished looping through all of our neighbors or traveling the current state of the queue, we'll add one value to our step. Step plus equals 1. And well, remember we want to return the number of steps. So if the node equals n minus 1 is the goal, we'll return steps. And if you recall, notice how our initial state goes from 0 to 1, 1 to 2, 1 to 3, 1 to 3 to 4. There is always an answer. So this will always give us a result. And I think we're good here. Let me run it. Okay, did I spell something wrong? I apologize. Let's try that again. Did I spell something wrong again? Oh, I have an initialized result, so let's do that. Apologize again. Okay, so looks good. And let me just submit it. Okay, looks good. I'm going to make a little change real quick. Personally, I wouldn't do this here, so I would do something like this. Something I would do, and what else? Maybe that's okay. I think the rest is fine. You just submit it again. I'm not sure it makes much of a difference, but it's just something I would do. Okay. As I mentioned earlier, in a short while I'll be uploading the dynamic programming approach, which will probably be much quicker as far as our complexity runtime. Other than that, if you liked the video or it was in any way helpful or educational, give it a like or a thumbs up, and or subscribe. Have a great day, and I'll see you next time. Bye-bye.